Our next scholarship winner is Hugo. Is that right? Hugo Villalobos, and he's from New Mexico State University. I'm sorry, I had all my notes, so I kind of got thrown off here. But to make this presentation is going to be Jim Joyner from Keystone Consultants, and Jim's going to come up and present the check and say a few words about his firm.
Thank you.
Thank you, Jim. Good.
Yeah, hi, I'm Jim Joyner, President of Keystone Consultants. We're a civil engineering, surveying, GIS, and mapping company, predominantly in the natural gas field for the last 25 years. So appreciate Mark putting on this conference the last few years, and we're really excited about having an opportunity to help out young graduates in this case. So congratulations, Hugo.
Thank you.
Okay. Okay, thank you.
Well, actually, my short name is Hugo Rojas. Rojas is my first name. So it's because I put all my full name in this case. Winker. Read.
Yeah.
Yeah. Okay. I'm a little bit more nervous than in my comps the past 3 weeks ago. So my research is focused in three topics. I will be talking about my first topic, that is 3D modeling using 4 techniques.
Probably need to work it off the keyboard.
All right. Sorry, buddy. All right, let's see what we got here. Here we go.
Okay, first, I will talk about the this region is in Chihuahua, the site of my research. This is a shallow lake that the extension is 100 square kilometers. It's in the basin of Laguna de Bustillos, where in this area the agriculture is the bigger support of this the economy of this region. So the problem is when that in these days this aquifer is overexploited. So for the government, this basic that
You don't have to advance it. Try to find it on the computer.
no.
All right.
Did Maurice have a lot of PowerPoints open? They might be eating up all the memory.
Well, it's closed. Sorry, everybody. Give us just a second here. We'll get this straightened out.
Okay.
Is it working? Yeah. So now you can. I don't know if you can use that.
Yeah.
button.
Okay. Okay.
All right.
This is only like the pointer. So the groundwater balance of this aquifer from Cuauhtémoc, Chihuahua, according with the government, the infiltration is 150 million of cubic meters. but the extraction by the wells are 311 millimeters of cubic meters. So it's a big drill coming from for irrigation land. According with the REPDA, the Public Registry of Water Rights, the concession is 311 millimeters of cubic meters. But the same, the National Commission of Water, they did some research about how many wells are in this area and how much water is are pumping, the farmers are pumping. So the reality is they are extracting 5 times the water that they have to extract. It's a big issue in our area. So according with this, the Mexican official standards, there's no a technical way to measure the volume of the water in the water bodies as a part of the water cycle, and they don't mention the technique to evaluate the evapotranspiration in the ag areas. So my dissertation is divided in 3 topics: the 3D model of the topography, the forecasting water storage change and the expansion in the sides of the lake, and the validation and regression analysis of the earth engine evapotranspiration flux measurements. So the 3D modeling is taking 4 sources of data. The first one is the bathymetric points. ABPs means altitude of the bathymetric points. The Euler data, that is satellite image, remote sensing, with the ABPs. The cloud points extracted by using drones. And the cloud points from INEGI. INEGI is the official government from geography information. So these 4 sources are processed in EnerGIS, and we can get the regional DTM and then the 3D model. So the bathymetry is linked with the corresponding high level, the contour. The Euler data is I'm extracting the contours using images from the past and link it with the altitude, the contour, and the cloud points are using the triangulation images, and the Mexican official then. So this is one example. This is the cloud point from the DTM from INEGI. This is the area that the drone is passing to get all the cloud points. And the Euler data and the ABPs are working together to find the contour with ancient or images from 10 years ago, for example. So we are using this one of the students from Ciudad Juárez University, and we are using a GPS RTK from Sophia, and this is a prototype I built to measure the bathymetry using a solar panel. That was supported by URI, the Water Research Institute from Mexico. It was a grant. So I used a DGA Phantom 3 Pro to get the pixels to extract the cloud points. This is a schematic function to get the bathymetric points the altitude of bathymetric points, but this measuring the depth, taking account the depth of the sensor, the sonar, and the RTK is used to get the altitude above the sea level. So it's an arithmetic conversion to get only the point as a topographic point. So this is the lines, or the paths of the surveying when the boat goes into the lake automatically until the third. This is the third path or travel of the boat. But the boat, the lake is very shallow. In the shore or near the shore, I mean near shore is like more than 1,000 feet from the shore. The water is like 1 feet. It's very, very shallow to a big lake like this, 100 kilometers, square kilometers, and the average is from 1.2 to 4 meters, the average. So when you are traveling, in that time, I got the deepest part, like 1.7, 1.8 meters. So when prototype arrives to the shore, the bouncing, the boat hit the bottom of the lake, and the propel hit the bottom and was lost. So I had to ask help a fisherman with a boat and with a troller, electric troller. Pulling the boat. So I had to do something in that moment because all the parts I had to buy it from internet. So the time was an issue. So the rest of the measurements was in a fisher boat. That was the ABPs. This is the other technique that I use is using the Sentinel-2, the European satellites, and I had to use the modification or normalize the difference water index. That with this information I can extract the water body and delineate the contour of the lake. In this case, I got the image from 2012, and I used the MNDY, and I drew all the contour for that time. As you see, the lake was shrinking in this time because it was a very extended drought from 2012 to 2013. You cannot see because I tried to show you the evolution and how is working the method with the MNDWI. And how I got the contours along the time. But the lake was completely dry in 2013. So the MNDWY from Landsat 7, I got the green band, I think it's minus the SWIR, the thermal one, divided by the sum of both bands in this place. So if you see the altitude of bathymetric points, I'm linking or taking that ABPs where the contour is crossing, is intersecting. So this elevation will be fixed with this dating of the soils, the accumulation of the sediments that they send these samples to Mexican University, that they have the special equipment to date the sampling soils. So this is the first, some of the anticipated results. Using all these points, even the RTK survey, I built the 3D modeling of this lake. It's important to say that I'm working in the imagery because it's very extensive area surrounding this lake, and I have to process all these points and images from in pieces, because using the normal software like a soft software photoscan needs a lot of resources from the hardware, and there are a lot of another software. It's open source. It's an open drone map that I can use, but I'm exploring how to process all this information through AWS, the Amazon Web Services, to increase the performance. So the other topic of the second article is based in the first one. When I got the 3D model, I will perform sediments, a runoff sediments to cover all the bottom part of the lake. So the theory is when the sediments is coming here, the water is displaced in the surrounding areas, flooding the agriculture crops. This is very, very new data from 10 days ago. So this is the accumulation rates in the lake and the years that they are coming. This is related, I think, because I need to prove this accumulation sediments are coming from the mountains surrounding the basin. The basin is an endorrheic. In the endorrheic basin is a closed basin, and there are a lot of deforestation surrounding because the pattern of the rain is going down, the trend is going down, but the sediments is going up. So what's happened is probably that the deforestation is affecting the soil. The soil is start to be more free, and the water, the torrents, the big rain takes that sediments into the lake, and the volume of the lake is increasing. So using the GIS, I take the contour, the last contour of the lake, and I give a thickness of sediments to the model. In this way, I increase the altitude of the bottom, and I simulate the volume of water that is coming from the runoff, and the sediments are depositing in the lake. So taking that date, the previous slide, I can adjust the amount of sediments from 2012 to 2016 to fix to update the level of the water, the ABPs. This is the schematic process to get the volume from the water level. I can take 3 points or sources of the edge of the water. One is using a GPS arcade to get the altitude and put in the layer and process it using these tools in EnerGIS, Polygon Volume 2. So the other one is to get a GPS, normal, or your cell phone, to stay in the edge of the water, get the point. So the accuracy of the cell phones are in 3 meters, around 5 meters, but that doesn't affect the calculation because the point you are need to be taken in the lake is in the flat part. I mean that part has a slope of less than 0.2 degrees. So it's so flat. So doesn't matter if you are 10 meters there or 10 meters here. The elevation doesn't change much. And the other one is take the most recent image and take the point using the previous technique using MNDWI. Get the point and put in the computer to get the volume of the water at this specific elevation. Now, if you are a hydrologist, you are calculating the volume of water with a time return of the water. So if you calculate how much water I'm forecasting, I can use that volume of water and put it here. So the process, all this process, I program it in Python, but this is the easy way to understand. This is the hypothetical water level of the water, the runoff volume, the simulation. This is the start. I start from here to calculate the volume. So with the same technique or tool in EnerGIS, I assign an arbitrary level, a little bit centimeters above the bottom, the deepest part, to calculate the volume of water below this line. If this volume is not equal to the volume taken from the runoff or SWAT or this hydrologic simulation, the level is increased to the next level. Increased by 1 meter. So I increase by 1 meter, doesn't fit, 1 meter, doesn't fit, until I pass the hypothetical level. This is more than I think will be according with the volumes. So when I reach this part, start to go down by the half of the previous step. The step is in 1 meter, but I cross the line, I divide it by 2, and go back to calculate the volumes. They calculated in this moment, and they calculated by the hydrologic volume in the simulation. So this is the water from I calculated in the solid lines, and this is the volume of the hydrologic simulation. So I'm going down by the step 5, and when I cross, I do the same. I divide by 2 and go up, and go down, go up, go down, go up, go down. until the threshold, I mean the percentage between them are less than 1% or 1%. The volume, the threshold I decide to fit in that line. Well, the third article is using Landsat and Landsat 7 and 8 that is taken from e-flux processes to get the evapotranspiration, taking some sampling points and compare it with in situ measurements. So I will perform a linear regression and empirical Bayesian. Yes, this is more new for me. The kernel to validate these points and to fit in this area. It's a more complicated thing to explain in some minutes. So thank you. If you have questions.